let us discuss few points regarding diagonal relationship between lithium and magnesium. See, lithium, the first element of 1A group, it resembles diagonally with magnesium. In most of its properties, lithium resembles magnesium. On similar lines, I can say beryllium of second group, this is 1A group, this is 2A group, this is 3A, you have 4A group, carbon, silicon. These two elements, beryllium and aluminum, they resemble diagonally, and then boron and silicon. So there are three diagonal pairs: lithium magnesium, beryllium aluminum, and boron silicon. These three diagonal pairs are present in the periodic table, only three diagonal pairs. Lithium resembles magnesium diagonally, beryllium resembles aluminum, boron resembles silicon of fourth group. Now, why do they resemble and what are the properties in which they resemble each other? Let us discuss now. Please look at the diagonal pairs once again. There are three diagonal pairs in the periodic table: lithium, magnesium, beryllium, aluminum, boron and silicon. The resemblance in the properties of lithium and magnesium arises due to similar polarizing power of Li plus and Mg2 plus. Li plus and Mg2 plus, their polarizing powers are similar, their ionic radii are similar. That is the reason why their properties are similar. The similarities are number one, their oxides and hydroxides are weak bases. Their oxides and hydroxides are weak bases. I mean, lithium oxide and magnesium oxide, lithium hydroxide and magnesium hydroxide, these are weak bases. Number two, their halides are deliquescent. Deliquescent means, I told you, they absorb moisture from atmosphere and they dissolve in the moisture to form saturated solution. Their halides are deliquescent and exist as hydrates. MgCl2.8H2O, LiCl.2H2O. Look at this formula: LiCl.2H2O, MgCl2.8H2O. Their halides exist as hydrates. Their halides are deliquescent. Look at the similarities. Their oxides and hydroxides are weak bases. Their halides are deliquescent and exist as hydrates. Another point of similarity: they react with nitrogen. Both the elements can react directly with nitrogen. Lithium forms lithium nitride and magnesium forms magnesium nitride. Another point of resemblance is regarding their carbonates. Their carbonates decompose on heating. Whether it is lithium carbonate or magnesium carbonate, when heated, they decompose to give corresponding metal oxide and carbon dioxide gas. So these are few points regarding diagonal relationship between lithium and magnesium. Let me repeat this: lithium of 1A group resembles magnesium of 2A group diagonally, and this similarity arises due to the fact that Li plus and Mg2 plus have similar size, their polarizing powers are similar, and this is responsible for similarities in some of their properties. Their oxides and hydroxides are weak bases, their halides are deliquescent and exist as hydrates. Both the elements are capable of reacting directly with nitrogen to form nitrides. Their carbonates decompose on heating to give carbon dioxide. That completes diagonal relationship. Compounds of sodium. Number one in the list is sodium carbonate. It exists as a decahydrate, Na2CO3 dot 10H2O, popularly called as washing soda. Let's learn about preparation of washing soda. The method we are going to discuss is solvay ammonia process. The raw material used in this method, we need limestone. This will act as a source of carbon dioxide. NaCl, that is taken in the form of brine, a solution of sodium chloride. We need ammonia also. Let's see the reactions involved in this process. Ammonia and carbon dioxide are bubbled into a solution of sodium chloride. Ammonia and carbon dioxide gases are bubbled in a solution of sodium chloride. These two gases combine and get NH4 taken twice, CO3. This is ammonium carbonate. Then ammonium carbonate further reacts with carbon dioxide and you get ammonium bicarbonate. And then ammonium bicarbonate reacts with sodium chloride and you get NaHCO3 plus NH4Cl. Due to common ion effect of sodium chloride, sodium bicarbonate forms precipitate. I'll tell you once again, in aqueous solution of sodium chloride, we are constantly passing ammonia and carbon dioxide gases. Due to this, you get ammonium carbonate formed in the solution. It will not come out as a precipitate. It exists as NH4 plus and CO3 2 minus. On further passing of carbon dioxide, the carbonate changes into bicarbonate because the pH of the solution will be decreased, and then there is an exchange reaction taking place between ammonium bicarbonate and sodium chloride. The reason is low solubility of sodium bicarbonate. Because of its low solubility, it precipitates out and you can filter it out. When you filter it out, what is left out in the solution is ammonium chloride. We use calcium carbonate as a source of carbon dioxide. When you do this, calcium carbonate decomposes to give calcium oxide. This calcium oxide is dissolved in water to give calcium hydroxide, and calcium hydroxide is made to react with ammonium chloride to regenerate ammonia. So every time you need not use NIV ammonia gas can be regenerated every time. I'll just show you with the help of equation how ammonia can be regenerated, recovery of ammonia. I'll also explain you how carbon dioxide is produced. Just go through the reactions once. Ammonia and carbon dioxide react to give initially ammonium carbonate, which changes into ammonium bicarbonate on further passing carbon dioxide. And then the ammonium bicarbonate and sodium chloride, they exchange the ions and you get a less soluble sodium bicarbonate. That becomes the driving force for the reaction. The low solubility of sodium bicarbonate is the driving force for this reaction to take place in the forward direction. You can just remove this by filtration. What is left out in the solution is ammonium chloride. I'm going to show you how ammonium chloride can be transformed into ammonia once again. You can see this is limestone, which when heated produces calcium oxide and carbon dioxide. So we are basically using limestone as a source of carbon dioxide. Apart from that, the calcium oxide which is produced here is dissolved in water to produce calcium hydroxide. You know, calcium hydroxide is a reasonably strong base. It actually belongs to the category of strong bases. Now this calcium hydroxide is then made to react with ammonium chloride. The purpose is to regenerate ammonia gas. So you end up with CaCl2 and ammonia gas. This is how recovery of ammonia is done. Limestone is transformed into calcium oxide and carbon dioxide. Carbon dioxide is bubbled into brine solution. Calcium oxide is then dissolved in water to produce calcium hydroxide, which is used for recovery of ammonia, because you get byproduct ammonium chloride, which can be transformed into ammonia once again. Of course, you get water. Sodium carbonate is to be produced. See, in the previous reactions, we have seen that sodium bicarbonate is produced. Sodium bicarbonate, you need to simply heat it to get sodium carbonate. This is always possible. Any bicarbonate, when it is heated, gets transformed into carbonate, and you get carbon dioxide gas produced. You can recover it, and again you can reuse it. So sodium bicarbonate, which is formed initially, can be transformed into sodium carbonate by just heating. Now, one very important question arises here: can we adopt this method for the preparation of K2CO3? That is very, very important question. Can we adopt this solvay ammonia process for the manufacture of K2CO3? The answer is no. And the reason for this is KHCO3 is highly soluble. When compared to NaHCO3, KHCO3 is highly soluble and it will not form a precipitate and you cannot recover it. So the method cannot be adopted for preparation of potassium carbonate, as potassium bicarbonate is highly soluble. That completes preparation of washing soda, sodium carbonate. Now I'll just talk about few uses of sodium carbonate. One important use of sodium carbonate, as the name itself indicates, it is called as washing soda. One important use of sodium carbonate is in laundries. In laundries, sodium carbonate is used especially for softening of hard water. Another important use of sodium carbonate is in qualitative and quantitative analysis, and it can also be used in the preparation of sodium bicarbonate. Sodium carbonate can be transformed into sodium bicarbonate. We will be discussing under sodium bicarbonate. So one is sodium carbonate is used in the softening of hard water. It is also used in the manufacture of sodium bicarbonate, which is popularly called as baking soda. It is used as a reagent in qualitative and quantitative inorganic analysis. We will move on to next compound of sodium, that is baking soda. The formula is NaHCO3, baking soda. Baking soda, as already discussed in the previous section, baking soda is formed during solvay ammonia process as an intermediate substance. See, when you pass carbon dioxide gas and ammonia gas simultaneously in a solution of sodium chloride, that is brine solution, you get sodium bicarbonate precipitated out, which is filtered and recovered. Otherwise, you can prepare it from sodium carbonate also. It's just a matter of dissolving it in water and bubbling carbon dioxide. If you bubble carbon dioxide in a solution of sodium carbonate, it becomes sodium bicarbonate. This is how the reaction takes place. Bubbling carbon dioxide in a solution of carbonate gives bicarbonate. Let's learn about uses of baking soda. As the name itself indicates, baking soda, this is used in as a component of baking powder. Number one is in baking powder. In bakeries, they use it for making the bread or cakes fluffy. When this substance is present in the dough, during baking, carbon dioxide gas is evolved, which comes out and makes the bread or cake fluffy. And then this can also be used as a fire extinguisher. It It is because of its ability to produce lots of carbon dioxide, and carbon dioxide does not support combustion. So, fire is put off. Its ability to produce carbon dioxide is responsible for it to be used as fire extinguisher. Number 3, this can be used as an antacid. Sodium bicarbonate is a mild base and therefore can be used to treat acidity problem, as it is used as an antacid. This can also be used in effervescent drinks. Again, it is because of its ability to produce carbon dioxide bubbles, so it is used in effervescent drinks. That's about baking soda.